Hey everyone, welcome back to Control System Lectures. This is the third video in our discussions related to feedback linearization. All the concepts which I am going to discuss in here was introduced in the previous lecture, and I strongly recommend you to watch that video first before starting this one. So let's start our lecture. In the last lecture, we had concluded our discussion on the case where relative degree of system output is equal to the dimension of state space. We have seen that in that case, the system is fully feedback linearizable. In this video, we are going to see the case where relative degree of output is less than the dimension of state space. Here also, we assume that we have a single input, single output system of the form x dot equal to f of x plus g of x into u and y equal to h of x, where f, g and h are sufficiently smooth in the domain D subset of Rn and f and g are mappings from D to Rn. Suppose the system has a relative degree k at x naught, that is relative degree of system is equal to k at x naught and k is strictly less than n, where n is the order of the system. N order of system or dimension of the state space. Here we set the first k functions just like we discussed in the last video, that is phi1 of x is equal to h of x, phi2 of x is equal to lf h of x, phi3 of x is equal to lf square h of x, etc. up to phi k of x, which is equal to lf k minus 1 into h of x. And also we said zi is equal to phi I of x, where I lies in the range 1 less than or equal to I less than or equal to k. So that way the coordinates till zk is set as z1 is equal to h of x, z2 is equal to lf h of x, z3 is equal to lf square into h of x, etc. to zk is equal to lf k minus 1 into h of x, where x is equal to phi inverse of z. Now we need to choose the rest of the terms, that is zk plus 1, zk plus 2, etc. to all the way up to zn. Well, as far as the new coordinates are concerned, if nothing else is specified, we cannot expect any special structure for these equations. So let me write this down as psi1, psi2, etc. to psi n minus k. Now, these functions represent the internal dynamics of the system, internal dynamics of the system, and the internal dynamics is of the order n minus k. Okay, now if I write the transformation matrix nu of x, we have nu of x is equal to phi1 of x, phi2 of x, etc. to phi k of x, psi1 of x, psi2 of x, etc. to psi n minus k of x. Then mu of x should have a Jacobian matrix dou mu of x by dou x, which is non-singular at x0. This is to ensure that the coordinate transformation in the neighborhood of x0 is smooth, and so is the inverse transformation. That is, it is a necessary condition for the mapping mu of x to be a diffeomorphism. Diffeomorphism. Moreover, we choose psi1, psi2, etc. to psi n minus k in such a way that Lg psi I of x is equal to 0 for all I in the range 1 less than or equal to I less than or equal to n minus k for all x around x0. The reason is, like I said already, the psi i's represent the internal dynamics of the system and therefore they are not explicitly coupled to the input u. If Lg psi I of x is not 0, then the term Lg psi I of x into u will appear in the equations. Then this will no longer be the internal dynamics by definition. Let me show this to you. If we choose psi I such that Lg psi I of x is equal to 0, then Zk plus I dot is equal to d psi I by dt, which is equal to dou psi I by dou x into x dot, which is dou psi I by dou x into f of x plus g of x into u. And this gives us Lf psi I of x plus Lg psi I of x into u. But we chose Lg psi I of x is equal to 0. Therefore, this term will be 0. So what is left is Zk plus I dot is equal to psi I dot is equal to Lf psi I of x, where x is equal to mu inverse of z, and of course I lies in the range 1 less than or equal to I less than or equal to n minus k. Therefore, we have our partially feedback linearized system. Z1 dot is equal to Z2, Z2 dot is equal to Z3, etc. to Zk dot is equal to Lf of x plus Lg Lf k minus 1 h of x, where x is equal to mu inverse of z is equal to v, and Zk plus 1 dot is equal to Lf psi 1 of x, where x is equal to mu inverse of z. Zk plus 2 dot is equal to Lf psi 2 of x, and x is equal to mu inverse of z, etc. to Zn dot is equal to Lf psi n minus k of x, where x is equal to mu inverse of z. If I define theta is equal to phi 1 of x, phi 2 of x, etc. to phi k of x, and this will be is equal to z1, z2, etc. to zk, and eta is equal to psi 1 of x, psi 2 of x, etc. to psi n minus k of x, which will be equal to Zk plus 1, Zk plus 2, etc. to Zn. Using theta and eta, we can describe the system of ours as theta dot is equal to a theta plus bv, and eta dot equal to some nonlinear function m of theta and eta, and y is equal to c theta, where a is equal to 0, 1, 0, etc. to 0, 0, 0, 1, etc. to 0, and etc. to 0, 0, 0, etc. to 1, 0, 0, 0, etc. to 0, and this is an n into n matrix, and b is equal to 0, 0, etc. to 0, 1, and this is an n into 1 matrix, and we have C is equal to 1, 0, 0, etc. to 0, and this is a 1 into n matrix. Now this equation represents the internal dynamics of our system. Internal dynamics of our system. Although the internal dynamics is not directly affected by the input, it does get affected through theta. For this reason, the internal dynamics is also called hidden dynamics or unobservable dynamics. Okay, so this is our input-output partially feedback linearized system. Now one question remains. Is the system stable? We can design V such that the dynamics described by theta is stable. However, we have to check whether the internal dynamics represented by eta is stable or not. For that, we study the zero dynamics of the system. Zero dynamics. So what is zero dynamics? What we do here is, by an appropriate choice of input, we maintain the output y at 0. I will repeat that again. By choosing an appropriate input, we maintain the output y at 0. This means that by providing some input, we maintain the output y is equal to h of x at 0. Note that we had defined z1 is equal to h of x, z2 is equal to z1 dot, z3 is equal to z2 dot, and so on. Therefore, this constraint means that z1 is equal to, z2 is equal to, z3 is equal to, etc. is equal to zk will be 0. That is, theta will be 0. As a result, the internal dynamics of the system will be governed by eta dot is equal to m of 0 eta, because theta is 0. The reason this is called zero dynamics is because we are zeroing the output. Once you zero the output, there is a part of the dynamics which is dependent on eta and is hidden. We don't want these eta variables to go unbounded. So, for our feedback linearized system to be stable, the zero dynamics of the system should be stable. That is, stable zero dynamics implies stable feedback linearized system. Now the stability of zero dynamics can be analyzed using the Lyapunov stability analysis we studied through lectures 15 to 20. Okay. Also please note that this stability of zero dynamics only ascertains the local stability of system, and we can't conclude anything about the global stability. Now let us see an example so that we get a clear idea of the concepts discussed so far. Consider the system x1 dot equal to minus x1 plus 2 plus x3 square by 1 plus x3 square, x2 dot equal to x3, x3 dot equal to x1 x3 plus u, and y is equal to x2. As you can see, the system is third order, so our n is equal to 3. Now let us find the relative degree of the system. Our output is y is equal to x2. Differentiating the output, y dot equal to x2 dot, which is equal to x3, and you can see that u is not explicitly appearing in this equation. So differentiating again, y double dot is equal to x3 dot, which is equal to x1 x3 plus u, therefore x1 x3 plus u. U is explicitly appearing in this equation, so the relative degree of output is k is equal to 2. The system is third order, meaning we have internal dynamics of the order internal dynamics of the order n minus k is equal to 3 minus 2 is equal to 1. So we need a transformation matrix. Mu of x is equal to phi 1 of x, phi 2 of x, and psi 1 of x. Okay, we usually define phi1 of x as y and phi2 of x as y dot, and also setting zi is equal to phi I of x, where I lies in the range 1 less than or equal to I less than or equal to k and k is equal to 2. Therefore, we have z1 is equal to x2 and z2 is equal to x3. And we have here z1 dot is equal to z2 and z2 dot is equal to v by setting u equal to v minus x1 x3. So our equation for theta dot is theta dot equal to a theta plus bv and y is equal to c theta, where a is equal to 0 1 0 0, b is equal to 0 1 and c equal to 1 0. And also keep in mind that we had defined theta is equal to phi 1 of x, phi 2 of x. Okay, now we need to find the internal dynamics of the system. For that, we need to find the third function psi 1 of x. Also, we learned that psi should be chosen such that Lg psi equal to 0. This is to guarantee that the internal dynamics doesn't depend on the input u. We can expand Lg psi as dou psi by dou x into g of x. So what is g of x of our system? For that, let me copy and paste our system here. Okay, so we can write our given system as x1 dot x2 dot x3 dot is equal to minus x1 x3 x1 x3 plus 2 plus x3 square by 1 plus x3 square 0 and 1 into u. So this is our f of x and this is our g of x. Now using this relation we can write dou psi by dou x1, dou psi by dou x2, dou psi by dou x3 into g of x, which is 2 plus x3 square by 1 plus x3 square 0 1 is equal to 0, and this yields us 2 plus x3 square by 1 plus x3 square into dou psi by dou x1 plus 1 into dou psi by dou x3 is equal to 0. We need to solve this differential equation to obtain psi, so that our coordinate transformation nu equal to phi 1 of x, phi 2 of x and psi 1 of x is complete. Now since we have only one psi, I am neglecting this subscript 1 and simply writing it as psi of x. Here also I am writing it as psi of x only. Okay, now this equation can be solved using separation of variables. Let us first assume a solution of the form psi equal to m1 of x1 plus m2 of x3. Therefore, the partial derivative of psi with respect to x1, dou psi by dou x1 will be dm1 by dx1, and similarly dou psi by dou x3 will be dm2 by dx3. Substituting these two into our differential equation, we have 2 plus x3 square by 1 plus x3 square into dm1 by dx1 plus dm2 by dx3 is equal to 0. This again implies 2 plus x3 square by 1 plus x3 square into dm1 by dx1 is equal to minus 1 into dm2 by dx3, right? Now to solve this, let us assume dm1 by dx1 equal to minus 1 and dm2 by dx3 equal to 2 plus x3 square by 1 plus x3 square. Therefore, we have dm1 by dx1 is equal to minus 1 and dm2 by dx3 is equal to 2 plus x3 square by 1 plus x3 square, which is equal to 1 plus 1 plus x3 square by 1 plus x3 square, which will be 1 by 1 plus x3 square plus 1. Therefore, this equation can be written as dm1 is equal to minus dx1. Integrating on both sides, we have m1 equal to minus x1 plus c1. Similarly, on this side, we have dm2 equal to 1 by 1 plus x3 square plus 1 into dx3, and integrating on both sides, m2 is equal to tan inverse x3 plus x3 plus c2. So we have psi equal to m1 plus m2, which is minus x1 plus x3 plus tan inverse x3 plus c1 plus c2. Now we know that psi of 0 is equal to 0 because the origin, which is an equilibrium point in our original coordinates, should also be a 0 in the new coordinates. Or in other words, the equilibrium point at origin in the original coordinates should be mapped into the origin of our transform space. Therefore, using this relation, we get c1 plus c2 is equal to 0. So psi is equal to minus x1 plus x3 plus tan inverse x3. Therefore, our mapping mu of x is given by x2, x3 and minus x1 plus x3 plus tan inverse x3, and this is equal to z1, z2 and z3. Also remember that eta was this matrix of size, and here we have only one psi. Therefore, our eta dot is equal to simply psi dot. And earlier we had seen that psi dot is equal to LF psi of x. Therefore, we have psi dot equal to LF psi of x. Therefore, we have eta dot is equal to psi dot is equal to dou psi by dou x into f of x, which is dou psi by dou x1, dou psi by dou x2, dou psi by dou x3 into f of x. And what was f of x? F of x was minus x1, x3, x1, x3. Therefore, minus x1, x3, x1, x3, which is equal to dou psi by dou x1 is minus 1, dou psi by dou x2 is 0, and dou psi by dou x3 is 1 plus 1 by 1 plus x3 square into f of x, which is minus x1, x3, x1, x3. Therefore, we get eta dot equal to psi dot equal to x1 plus x1, x3 plus x1, x3 by 1 plus x3 square, which is x1 into 1 plus x3 into 2 plus x3 square by 1 plus x3 square. Okay, so now we have theta 1 is equal to phi 1 of x, which is equal to x2, theta 2 equal to phi2 of x, which is equal to x3, and eta is equal to minus x1 plus x3 plus tan inverse x3. And using these three, we have x1 is equal to minus eta plus theta 2 plus tan inverse theta 2. Therefore, we have eta dot is equal to minus eta plus theta 2 plus tan inverse theta 2 into 1 plus theta 2 into 2 plus theta 2 square by 1 plus theta 2 square. Therefore, our full system is theta dot equal to 0, 1, 0, 0 into theta plus 0, 1 into v eta dot equal to minus eta plus theta 2 plus tan inverse theta 2 into 1 plus theta 2 into 2 plus theta 2 square by 1 plus theta 2 square, and y is equal to 1, 0 into theta. Now if we need to check the stability of the system, we check the zero dynamics. Therefore, plugging theta is equal to 0, that is theta 1 equal to 0 and theta 2 equal to 0, into this equation we have eta dot equal to minus eta, and we have seen that eta is equal to minus x1 plus x3 plus tan inverse x3, and x3 is eta 2, and we have set eta 2 equal to 0. So the only term remaining is minus x1. Therefore, this equation translates to x1 dot equal to minus x1. So we have x1 dot equal to minus x1, which is dx1 by dt is equal to minus x1, which gives us dx1 by x1 equal to minus dt, and integrating both sides gives us ln x1 is equal to minus t plus c. At t is equal to 0, we have x1 of 0. Therefore, ln x1 of 0 is equal to c, and therefore we have ln x1 is equal to minus t plus ln x1 of 0, and this one rearranging gives us ln x1 by x1 of 0 is equal to minus t, or x1 is equal to x1 of 0 into e raised to minus t. Here we have e raised to minus t, which means that these dynamics will die out as time progresses. That is, eta variables will die out as time progresses. So our system is stable. So that is how we implement the procedure for input-output feedback linearization. Okay, that's all for this lecture. Since this concept requires a clear understanding of the topic, please do watch the video till you are able to grasp it properly. For those who are interested to study this topic in detail, I refer the book Nonlinear Control Systems by Alberto Isidori. From the next video onwards, we will start our discussions on optimal control. Thanks for watching and have a nice day.